This is a long line of functions.
No.
We're going over circular and periodic functions.
Highlighting things she's highlighting.
No, now it's just in the way.
No, it's not.
Yes, it is.
Don't do it. It's in the highlight.
Where's the
Will you
spot?
stop?
Ethan, what are the odds?
All right, so
We've been over this already, so.
we're gonna go over a unit circle. Okay, unit circle is a circle with a radius of 1 unit centered at the origin on the coordinate plane. Okay, if you hear me say unit circle, shh, hey, sit down now.
Unit?
Well, you are sitting down. Move to your desk.
Wrecked.
Move to your desk. Away from the board.
Desk,
Ottoman.
sir.
All right, so you can use a point P on the unit circle to generalize sine and cosine functions.
Get over here.
So
It's not gonna
sine,
come off.
shh, guys,
Tell him to friggin' stop.
stop,
He's raining on my bottle.
stop.
Come on. It does come off. So they're like wiener.
Can we stop now? Hey, guys, I need you to focus. We still have to get through this stuff. So sine of theta is equal to y over r. We did go over that before in one of our previous sections. So since our radius of this unit circle is always going to be 1, sine of theta is just y over 1 or y. Okay? Cosine of theta was equal to x over r. Again, your radius in a unit circle is always 1 unit. Okay, so it'd be x over 1 or x. So the values of sine of theta and cosine of theta are the y coordinate and the x coordinate respectively of the point where the terminal side of theta intersects the unit circle. So both cosine of theta equals x and sine of theta equals y are functions of theta. Because they are defined using a unit circle, they are called circular functions. So in example 1, where the terminal side of angle theta in standard position intersects the unit circle at point P. Okay, point P is at square root of 7 over 4, 3/4. And we want to find all the 6 trig functions of theta. So that's sine, cosine, tangent, secant, cosecant, and cotangent. Okay, those were our 6 trig functions. So in our coordinate point, you have x and y, correct? Okay, your x coordinate, your y coordinate. Well, the sine of theta is going to be equal to your y coordinate. Okay, so sine of theta is going to be your y coordinate. So it's just going to be 3 over 4. Your cosine of theta is your x coordinate. Okay, so that will be square root of 7 over 4. Okay, now to find tangent, I am going to graph this point P. So if you have your graph, okay, both of these are positive, so it is in this first quadrant here. So if I go square root of 7 over 4 and then up 3/4, it doesn't have to be exact, just as long as you're in the correct quadrant. Okay, you create this triangle here, okay, where theta is this angle. And to get to that point, I went right square root of 7 over 4. So that's the length of that side. Then the length of this side, I went up 3/4. Now your radius or your hypotenuse, since this is a unit circle, okay, is always 1. Okay, so that hypotenuse is always 1. So to find the rest of our trig functions here, I need tangent of theta. Okay, tangent of theta, if I go from my angle, tangent is opposite over adjacent. Okay, so my opposite side is 3/4 over my adjacent side is square root of 7 over 4. Okay, I'm going to multiply the numerator and denominator by that denominator's reciprocal. Okay, that way it cancels out that denominator. What? So that I can cancel out this denominator, because I don't want a fraction within a fraction, or a fraction over a fraction. So you multiply by the reciprocal so you can cancel out that entire denominator. So here I have 3/4 multiplied by 4 over square root of 7. Okay, when I do that, I have a 4 over a 4. So those 4's also cancel out. Okay, and I have 3 over the square root of 7 then. How do I simplify 3 over the square root of 7?
So now you got square root times, yeah.
Times by, yes. Okay, so you multiply by square root of 7 over square root of 7. You get 3 square roots of 7 over 7. So that would be your tangent of theta then. Okay, the other 3 trig functions are just those reciprocals. Okay, remember we have those reciprocals. So the reciprocal of sine is cosecant of theta. Okay, so just flip your fraction. Okay, so that would be 4 over 3. What? Did I grade yours?
Take it?
No. I just have to grade it. Yeah, you can get them back. Okay, then reciprocal of cosine is secant. Okay, so flip that fraction. So we have 4 over square root of 7. Again, you need to simplify that by multiplying by square root of 7 over square root of 7. You get 4 square roots of 7 over 7. And then the last one is cotangent of theta. Okay, so I'm going to look at this one that I got. Okay, that's 3 over square root of 7. And I'm going to take the reciprocal of that answer. That way I don't have to simplify again. So my reciprocal then would be square root of 7 over 3. Okay, so those would be my 6 trig functions using the unit circle. Okay, so if it says it's on the unit circle, again, your radius is always 1. Okay, so that hypotenuse of your right triangle is always 1. Questions? All right, so next we're going to look at a periodic function
That's all we have to do.
for that problem.
That's a lot. That's a
Yeah.
lot.
Just find the 6 trig functions like we've done in the past. Yep. Okay, so a periodic function has y values that repeat at regular intervals. Okay, so one complete pattern is a cycle, and the horizontal length of one cycle is a period. Okay, so in this picture here, one period would be this horizontal distance, okay, and it is one cycle. So you're looking to see where it repeats, okay, so where the pattern starts repeating again. So if I look at this one again, I would start at 1, okay, it goes down to -1 and back up to 1. Okay, so notice that it starts and stops at that same point, and then it repeats again. It goes down to -1 and back up to 1. Okay, so that distance would be considered 1 period. Okay, and that would be 360 degrees. Okay, and it would go again at 360 degrees. Okay, and that would be 1 period. Okay, so it repeats that same period over and over and over again. So example 2, we want to determine the period of this function. So if I start at 1, okay, go down to -1, it stays horizontal and goes across, and then it goes back up to 1. Okay, so it hits 1 again, and then you notice it does go again back down to -1. So in this one, if I start at the y-axis, it starts repeating when I hit this point right here. So the period then would be pi. Okay, so the period is going to be pi. So again, you're just looking to see where it repeats itself. So how long is that horizontal length where it repeats itself? Okay, questions on example 2? All right, then example 3. So the rotations of wheels, pedals, carousels, and objects in space are all periodic. Okay, so they rotate within that same pattern. So in example 3, the pedals on a bicycle rotate as the bike is being ridden. The height of a pedal is a function of time as shown in the figure. So we want to make a table showing the height of the bicycle pedal at 0, 0.5, 1, 1.5, 2, 2.5, and 3 seconds. Okay, so in our picture we do have these different heights here. So at 0 seconds, okay, 0 seconds is labeled up here. What is the height of that pedal? If it's at 0 seconds, how high off the ground is that pedal? 18 inches. Okay, then moving on to 0.5 seconds. Okay, rotating to here. How high is that? That's 11. Then to 1 second, that's right here.
1 second.
That's 4 inches. 1.5 seconds is back over here.
11.
That's 11. 2
18.
would be 18. 2.5, so again I
11.
rotated 2 to 0.5 here, would be 11. And then to 3, so rotate again another 0.5, that's 4. Okay, so it is periodic, it repeats itself over and over again. So we go from 18, 11, 4, 11, 18. And then we go 11, 4, 11, 18 again. Okay, so it repeats itself. So in letter B, we want to identify the period of the function. So where does it start repeating itself again? At how many seconds does it start repeating itself again? If I look at my chart here.
2 times.
At 2. Okay, so the period would be 2 seconds. Okay, so that's where it starts repeating. And that would be the time it takes to complete 1 rotation, is another way to think about it. Okay, so how long did it take to complete 1 rotation throughout? And that was 2 seconds. So the last part here is to graph our function. Okay, so we're letting the horizontal axis represent the time t, and the vertical axis represent the height h in inches that the pedal is from the ground. So we just have to use our table of values and plot these points. So our first one is at 0 seconds. At 0 seconds, the height of the pedal was 18 inches. So at 0, we'll go up to 18. Okay, and again, our horizontal here is the time, and our vertical is the height. just to label our graph a little bit here. Okay, then at 0.5 seconds, it was at 11 inches. So at 0.5, we'll go to 11. At 1 second, it was at 4. That's about here. 1.5 seconds, again, it went back up to 11. 2 seconds, up to 18. 2.5, again at 11. And then 3 seconds was at 4. Okay, so connecting here then, goes down, back up, and back down. Okay, so this is considered a periodic function. It repeats itself over and over and over again. Okay, and this graph further shows that 1 period would be 2 seconds. Okay, so you start at 18, go up or down and then back up, hit 18 again, and it repeats that same pattern. Okay, any questions on your periodic functions? How to identify the period, how to find your 6 trig functions given that it is a circular unit circle function.